Good evening. I am Shushmita Mandal. On behalf of the German Consulate in Kolkata, I welcome you all to the 6th web-based session of our science lectures. These lectures are organized, as you know, with an aim to further strengthen the cooperation and collaboration between Germany and India on science and research. Today, there will be again 2 lectures. The first lecture, The Universe as a Quantum Gravity Condensate and its Emergent Evolution by Professor Daniele Oriti. And the second lecture, Shadows, Echoes and Memory, will be by Professor Sayan. Professor Ranjan Ganguly will be the moderator of this session. And before we start, I would like to hand over to the German Consul General in Kolkata, Mr. Manfred Auster, for his introductory comments. Mr. Auster, please.
Thank you, Ms. Mendel.
Yeah.
And good evening to all of you. Herzlich willkommen, guten Abend vom Deutschen Generalkonsulat in Calcutta. Warm welcome to all the regulars, but hopefully also to one or the other newcomers in the show. And as Ms. Mendel rightly pointed out, this is a series that the Consulate has been organizing since 2016 already. Usually we did that in a live format. Well, we are live now as well, but online. It used to be one with people being present in the room. The pandemic doesn't allow that but it also gives us a chance to reach out even further to new audiences. And so probably once we can return to something resembling normality, we will certainly also keep the possibility to watch and follow these exciting news and lectures online. Having said that, again, it is a platform to share, a platform for scientists and researchers to share their findings with their peers, with academia, and also with lay women and lay men like myself, who can simply try to follow what the colleagues and the distinguished lecturers present. And I must say I was always fascinated so far by what you present us. And it's nice to step back as a humble lawyer, forget what's normally on your desk and try to follow something completely different. But before I hand over to our moderator of the day, I have the pleasure to make some announcements concerning the science community with whom we are working together. The first one is I would like to sincerely congratulate Mr. Sanjeev Rangras, who has been recently inducted in the Indo-German Science and Technology Center, the IGSTC, as a member of the governing board from the Indian side. Mr. Rangras is an alumnus of IIT Kanpur and is presently the group head, research and development, sustainability and projects of ITC Limited in Kolkata. Congratulations on that one. And also congratulating Professor Swadhin Mandal of the Department of Chemical Sciences, IISER in Kolkata, who has been awarded the prestigious Alexander von Humboldt Foundation Research Award, the Friedrich Wilhelm Bessel Research Prize. For the congratulations, gentlemen, for that. And for some of our new listeners, just a brief explanation that Alexander von Humboldt, whom you will hear some reference being made to tonight on several occasions, is the patron for our scientific research foundation that fosters all postdoc kind of science interaction from the German side. And we are really proud to have quite a lot of alumni from the Alexander von Humboldt Foundation here in India. All right, that was much more than I was allowed to time-wise in the first place. Let me hand over Professor Ranjan Ganguly for the introduction of our guests tonight. The floor is yours. Thank you.
Thank you, Herr Auster. It's a very different evening today because we have an esoteric subject as our point of or topic of discussion. But just to comfort Herr Auster, Probably, and getting that comfort from both the speakers this afternoon when we had a dry run, it's not going to be that esoteric. And in fact, as a child, we all asked the questions, twinkle, twinkle, little star, how I wonder what you are. So probably our speakers will try to answer that very basic question we had as child. And this actually, I mean, being a power engineer, I'm sharing it with only this audience here. I had a deep-rooted connection with these questions also, because as a grade 7 student, I had trouble in understanding, or rather memorizing, that power equals I square R. It's a very basic equation, and I never could manage that. So my mom said that, well, there is a mnemonic you can use, twinkle, twinkle, little star, power equals I square R. So I like that. But in the exam time, when it came, you know, as Indians, we overdo things, prepare hard for the exams, and when the exam came, I repeated that, twinkle, twinkle, little star, how I wonder what you are, up above the world so high, power equals R square I. So I think we would get some insight so that we don't overdo things. And on a more serious note, this field of cosmology is probably the first sign of man's trait with science, or inquisitiveness, which actually led us to explore beyond the terrestrial thing. And I mean, there was no need for human being in the beginning to look for or ponder over the origin of the stars, but still we did. And that's why the science, the frontier of the science, is progressing. So it's a very important topic, and I thank Sushmita for choosing this topic. And also, I thank Professor Oriti Bhattacharya to essentially link us to those speakers. Now, without a further delay, I would like to introduce you to our first speaker today, Professor Daniele Oriti. I hope you can see the screen. Is it visible? Professor Daniele Oriti is a senior researcher and a Heisenberg Group leader at the Arnold Sommerfeld Center for Theoretical Physics, LMU Munich, Germany, where he directs a research group on quantum gravity and foundations of physics. A PhD graduate from the University of Cambridge, UK, he has held research positions at University of Cambridge, Utrecht University, and Perimeter Institute, Canada, and visiting or adjunct professorships at University of Waterloo and University of Hamburg. Professor Oriti has also directed a research group at the Max Planck Institute for Gravitational Physics in Potsdam, Germany. He works in the field of quantum gravity, focusing prominently on the issues of emergence of continuum space-time and geometry from the fundamental theory. He is a main proponent of the tensorial group field theory formalism for quantum gravity, and has pioneered a novel approach to fundamental cosmology from quantum gravity perspective. Author of over 100 publications in international scientific journals, Professor Oriti has received a number of awards for his research, including the prestigious Sofia Kovalevskaya Prize from the Alexander von Humboldt Foundation. So we have an illustrious speaker here. And I would request with this introduction to request Professor Oriti to take over the session. The session is all yours, Professor Oriti. I would, before handing over to Professor Oriti, I would like to request all the participants, remind them not to use the present now button, because that will basically abort the presentation from the speaker. So please don't do that. And also, if you have any questions that you would like to ask the speakers, there is a chat box, so you can put your questions at the chat box. We will be discussing, or rather addressing, the questions at the end of both the sessions, means after both the speakers have spoken. So in your questions, please address to whom you are asking the questions. With this brief note, I'd like to request Dr. Oriti to take over the section. Dr. Oriti.
Yeah, let me share my screen. Here we are. You see it? Is that okay? So I
Yes.
go full screen. Okay, cool. Thanks so much for the nice introduction. And indeed, I want to discuss about the universe, which is obviously quite a big topic. I'll not go into any technical detail. What I would say is the main purpose of the presentation is just to convey the motivation and somehow share a bit of the enthusiasm for the questions we are trying to address, more than any of the specific results or let alone any technical aspect of the story. So because of this, I want to make, first of all, very clear one point. So we're going to talk about what I think is cool stuff and things that many skilled scientists have discovered about our universe. So the list starts a long time ago and includes many, many prominent people up until recent times. And moreover, I'm going to talk about some mysteries that other quite brave scientists are currently investigating. But it is very important, I think, that we keep in mind a crucial aspect of what it means to be a scientist and to do science, just to put everything in the right perspective. Scientists are just like kids. That's the main point. So in fact, they are like sort of grown-up kids who manage not to grow up too much. What I mean is that the same things that kids do, like constantly looking around, investigate the world, being curious about everything, and then imagine possible worlds and impossible ones as well, play with objects to see what they do, just for the fun of it, just to discover what happens if you smash things or if you roll things and so on, and then make up stories about what they observe to make sense of it. And most important, well, they construct things. Well, that's basically the same things as scientists spend their time doing, just with more sophisticated tools at the linguistic, conceptual level, and of course at the technological level. So what is the scientist started doing since the beginning of times? Well, they look at the skies. And in fact, recently they managed to look far away and then farther away at the galaxies and beyond. And in fact, they had to do it with appropriate tools. That's really, in a way, together with the use of mathematics that I will mention later on, and a bit of some more serious attempt to stay rational, the main difference with what kids do. And Hubble, when he pointed the telescope, a sophisticated one, to the skies, at the galaxies, discovered something quite surprising. In a sense, that was the beginning of physical cosmology, or cosmology as a science, at the more experimental level in many ways. Well, it discovered, for example, that galaxies are moving away from each other, and in particular, they're moving away from us. Moreover, the more distant they are, the faster they move away. And this, of course, is a puzzle. It's something nobody was expecting, and of course, something that nobody had observed before. Moreover, in the meantime, we also started to open the ears to the universe, just listen. So we do it as humans in general, and scientists decided to do it just with more sophisticated tools again, starting a long time ago, already with very sensitive ears. And what happened when Penzias and Wilson in the early 60s started to listening to the skies, to the universe, well, they also got more surprises. They started hearing some feeble sounds. Well, strictly speaking, they were not sounds. It was a very long wavelength electromagnetic radiation coming clearly from very, very far away. Well, at the beginning, they just didn't know where they were coming. They thought they were pigeons who had nested in the antenna. They thought they were the cars in a nearby city. After they excluded all these possibilities, it turned out that these sounds, these small disturbances in the antenna, was coming from very far away, beyond the solar system, in fact, beyond all galaxies. And that means that it was coming from long time ago, because it took a long time to reach us from wherever it was emitted. And moreover, it was coming uniformly from any direction they were pointing the antenna towards in the sky. One more big puzzle. So just like kids, you find puzzles, you try to make sense of them. And so we were presented with some weird facts, some mystery to solve. And so it was up to the scientists to play, to solve it, to make sense of that. So they had to make up stories that were imaginative, because clearly they were discussing stuff that was not part of everyday life. So you had to be quite imaginative to make sense of that. At the same time, you had to be credible and rational. Your story should be solid, quantitative, and coherent. And they should say more about the world than what you put in them. Otherwise, they're sort of useless. If you just repeat what you observed, then you're not really explaining, you're not really making up a new story, you're just repeating the facts. So you have to have a reasonable storyline. You have to use mathematics, that's the language, because that's the language that allows you to make your story solid, quantitative, and coherent. And you have to be able to predict things. You should be able to deduce from what you observed and what your story is about that, what new things you should be able to observe is if you point your telescope, your tools appropriately in the sky or anywhere else in the world. So you have to do science. So people started doing science of this galactic and extragalactic facts. So they started doing the science of cosmology. You imagine scientists being like wise and deep Greek philosophers discussing and among them in a very polite, civil manner, just the epitome of wisdom. Or maybe like the scientists in the Renaissance, doing experiments and then thinking and again discussing politely with your colleagues and so on. Well, okay, that's also what science is about. Very often, that's actually what happens. The routine work of a scientist is more like just trying to make sense of something that really doesn't make sense to your poor mind. Discuss with your colleagues, which do not really understand much better than you, but maybe together you have a chance. And then you have to convince the other colleagues who are not really convinced of what your story is, what your explanation is. So that's science. The last bit in particular, it's a community effort. And when I say effort, it's really an effort. After many intellectual struggles, as well as fun, in fact, we had a story to tell about all those puzzling phenomena. We developed, and also that, despite a lot of anecdotes, it was in fact a community enterprise, was in fact a community effort. So Einstein was the main proponent, of course, the main developer, but general relativity is also a community product. And cosmology. So we had a science of the universe and its evolution. The main point about general relativity is that gravity is in fact to be understood as space-time geometry. So when we measure a distance between objects or a time interval between events or volumes and all geometric quantities out there, we are actually making statements about the gravitational field, about the gravitational force in Newtonian language. So moreover, it discovered that gravity not only is to be identified with space-time geometry, but it's a system, it's a physical system that interacts with the other physical systems, like material bodies, which deform space-time, so they change the geometry, and vice versa. Once you have a deformed, modified geometry, the motion of all the other material bodies is modified because they have to move on a different space, a deformed space. So this deformation of space-time, of the space-time geometry, is what we call gravity. This is the main findings of GR. And this deformation, so gravity itself, has its own dynamics, its own equations, its own life, you could say. It's not an inert background that sits there watching the world. It's active part of the world in itself. So that's the main lesson of general relativity. The main thing we understood on the theory side, from the theory that Einstein and colleagues developed. So how did that explain the phenomena? Well, again, the main lesson is that space-time itself is a physical system. So space itself can evolve, it can change in time, it can be affected by the other systems, and vice versa, it can affect other systems. So in particular, it was discovered that space itself can expand, and when it expands, it carries with it the other objects that are interacting with it, material objects. This was a particular solutions, particular configurations of the space-time geometry that solve the equations of general relativity were discovered by Friedman in the early 20s. And he discovered, in fact, that if you just look at space as if there was no matter, or if there is a very simple matter, and you look at it at a very large scale, so you look at the universe at large scale without looking at the details too much, then you can find solutions of the theory that describe that, in which the universe expands. In fact, there are several of those. The key point, therefore, is that any region to which you assign a volume will see that volume growing in time. That's what happens in the solutions of the equations. So this, in fact, explains what we see of the galaxies. You can think of it as an analogy, but in fact, it's quite close to what happens. So think of a balloon being inflated and draw galaxies on the surface of that. Then you inflate the balloon, and from the point of view of each galaxy, all the other galaxies are receding from it. And the farther away they are, the faster they run away. That's exactly what Hubble observed. So this is the explanation within general relativity of what Hubble observed about the galaxies. And it is due, so the story goes, this effect, what we see, is due to the fact that not the galaxies are doing anything, it's space itself which is doing something. It is expanding in time. Well, after a lot more science, more calculations, more observations, a lot of debates, but also a lot of amazement. These are the observations, the calculations, the debates, and the amazement in this order. We have a detailed picture of the universe, thanks to general relativity and the other physical theories that have been developed in the meantime, quantum field theory in particular, and the standard model. We in fact obtained a detailed picture of the universe from the very infancies to the whole evolution so far. So the universe expanded from a very dense, very hot, very small state and kept expanding. And the more the mass energy content became diluted, then we had 4 atoms forming, then stars, then galaxies, and then we came along. We have, in fact, a detailed picture of the story of the universe, which is also the story of space itself. So the other puzzle, what Penzias and Wilson observed, was also explained. How? Well, what they actually heard, or what they detected with their antenna, is the so-called cosmic microwave background radiation. Many words to say something, in fact, rather simple. At the beginning of the universe was very dense. Not even light could really propagate. It was quickly absorbed by matter, by the mass energy density that was around. When it became diluted enough, and therefore large enough, light could propagate without being immediately absorbed. Well, what Penzias and Wilson observed or heard or received was the first light on collective dynamics of something else. So this is what many current approaches to quantum gravity, in fact, are suggesting to be the right perspective on the problem of the universe and of the Big Bang as well. So it's a problem very similar to the typical one in condensed matter, when you have the atoms and you have to reconstruct macroscopic behavior. These are the constructions. Now we are thinking about building blocks that we have to assemble, whose properties we have to study, and from which we should construct something. And what we have to construct is the universe. Space, time, and the universe, with the same strategies, and hopefully with the same results. So several approaches to quantum gravity have been developed. I'm not going to mention any of them, well, not any of them in detail. And there are lots of suggestions, more insights and doubts and confusion, but also many results and new understanding. I'm going to mention just one last suggestion in, I think, my last 2 minutes. I only mentioned one recent suggestion about how to solve the puzzles about the beginning of the universe and the emergence of space and time and cosmology within a more fundamental perspective of a quantum gravity formalism. I'm discussing in particular a suggestion that is partially realized in one particular quantum gravity approach, but with several connections to other approaches. So there are several shared structures and ideas in common. The approach is called tensorial group field theory, and I speak about that because it's the one that I know more and because it's the one that I find more promising, and well, because I have to choose something to work on and to tell you about. The idea, the suggestion is that the correct way of looking at the universe and reconstructing or obtaining a universe and a space-time that changes, and general relativity and all of cosmology from within a quantum gravity formalism, is to see the universe as a sort of a condensate of the building blocks that the quantum gravity formalist proposes as the fundamental entities. Here, the building blocks in this particular formalism can be pictured as quantized simplices. A simplex is just like a little cell. In 2 dimensions, it would be a triangle. In 3 dimensions, which is the dimensionality of space, as we are observing it, is a tetrahedron, a little pyramid with triangular base. These are the quanta of space, the basic building blocks of space. They are quantum, and they do not live in any space. So though in the picture, of course, I put them in some embedding space, in some environment, the way you deal with them in the mathematics of the theory is without embedding them anywhere. Why? Because they have to reconstruct space. They cannot be defined in terms of some embedding space. And the theory describes how they interact, how they form extended structures, how they change properties, and so on. In particular, it should also describe how they collectively interact in large numbers to constitute, to give rise to a continuum universe, a continuous universe as we usually describe it in cosmology. And this suggestion is the way they give rise to such a universe is through a process which is pretty standard in many body physics, in condensed matter and solid state and so on, which is a sort of a condensation. And because this condensation process will produce our standard notions of geometry, then it has been dubbed geometrogenesis. So the universe should be seen as a quantum condensate, a Bose-Einstein condensate, to be a bit more precise, a quantum fluid made of the building blocks of this quantum gravity formalism. So just like water molecules in large numbers condense and then form the liquid we all know at macroscopic scales, in the same way, the building blocks of space, not living in any space, will interact in large numbers condense, maybe still with their quantum fluctuations, and then form space and time as we know them. And then the cosmology as we know it. So this is the process suggested by the theory. How does then generativity emerges and how does cosmology emerge? I close in 1 minute. So emerges from coarse graining, just like standard hydrodynamics emerges from the molecular dynamics. The idea is that cosmology will emerge as the hydrodynamics of the underlying quantum theory of gravity, the quantum theory for the microscopic building blocks. And in fact, it seems to work, at least in appropriate approximation for some models and so on. We recover the Friedman evolution of a very simple universe from the fundamental dynamics of the quantum gravity building blocks, exactly as the simplest type of condensate hydrodynamics. So many of the features of the universe as we know it can be found back from the fundamental theory with a number of approximations. So what does the theory says about the beginning? Well, it says the following about the beginning, about the origin of the universe. It says that if we stay at the level of the hydrodynamic description, which is an approximation, of course, a very coarse approximation, what we find is in fact a quantum bounce. We find that there's no Big Bang singularity, there's no pathological situation. The universe contracts as we go to the beginning, but then re-expands. So there's no real beginning in this sense. But also we have some indications that the hydrodynamic approximation may break down, and maybe something more radical, in fact, will replace the bounce, a proper disappearance of space and time, as I mentioned earlier on. So we don't really have all the answers. I'm sorry, I have to close the lecture without the talk, without giving you all the answers. We need a lot more work, new ideas, new skills, and new observations. But that's exactly what makes it interesting. I hope I emphasize this point enough, and fascinating and fun. So if you want to join in the journey, you are most welcome. But beware, we only allow to join curious, hardworking, and imaginative kids. Thank you so much.
Thank you, Dr. Oriti. That was a mesmerizing talk, I would say. And I'm really sorry that we just had only less than half an hour for you. But I think you did a great job in posing those very vital questions, because in science, as we all know, the questions are probably more important than the answers, because the answers follow the questions. So yes, we have had a handful of questions.
Sorry, on that I had an easy job because I don't have all the answers. So
Okay.
So, I mean, while we are still in the spell of this great talk by Dr. Daniele Oriti, we have an equally enigmatic topic waiting for the second half, and an equally great speaker is waiting in the queue. And before I hand over the session to Professor Sayan, the next speaker, I would briefly give an overview of our next speaker. So let me just pull up the slide. Just give me a second. Somehow I'm not. Okay. Let me share the entire screen at least. That will. Our second speaker, Professor Sayan, is Professor of Physics at the Indian Institute of Technology, Kharagpur, India. Professor Kaur did his PhD from IIT Kanpur back in 1994, and afterwards he did his postdoctoral stints at various places. Then he joined IIT Kharagpur in 1998. Professor Kaur has taught a wide variety of courses in IIT Kharagpur and also has worked and published in diverse research areas in physics. Professor Kaur specializes in general relativity and gravitation, with added interest in high-energy physics and quantum mechanics. He has been the secretary and president of the Indian Association for the General Relativity and Gravitation, which is known also, the acronym is IAGRG, and is also involved in its activities for many years. Professor Kaur will be illuminating us on a topic which he names shadows, echoes, and memory. I'm sure that it will be an equally mesmerizing session, and with this, hand over the session to Professor Kaur. The session is yours, Professor Kaur.
Well, let me first share my screen and let's see it works. Yeah. So can you see the slides?
Not yet. It's coming.
Yeah.
No, it's coming.
It's okay?
Yeah. Just to give you a reminder, generally we have a little delay in the system. So, I mean, while you explain or draw things or change the slides, expect a delay when it reaches the audience.
Well, I'm not going to draw much, so I may just use the pointer. So
okay.
Just that's
all right.
Nothing
yeah.
new. Okay,
Please.
so let me first thank the organizers, Dr. Ganguly, for his kind introduction, and as well as all those who were involved in inviting me and arranging this exciting session. We already had a wonderful presentation by the previous speaker, Professor Daniele Oriti. And I'm happy that he told you a little bit about space-time and space-time curvature, which will help me out a little bit as I give this presentation. So as you see, these are very simple words: shadows, echoes, and memory, which are familiar to every one of us. And these are commonplace phenomena. And let me just tell you what they are very briefly. All of you know all of this. We know that shadows are ubiquitous. They are there everywhere. They appear when there is light. So that is important. And shadow boundaries separate dark regions from illuminated ones. And of course, all of us know that the so-called solar and lunar eclipses, they involve shadows. So that's a little bit about shadows, familiar to everyone. So then we turn to echoes, and echoes are known for sound largely. Echoes are used for negative pattern, etc. Tone, for instance, and echoes also relies on ultrasonography, which are familiar with, echocardiography, imaging of human organs. All of these are related to the simple phenomena of echoes. So that's what echoes are. And we'll come back to all of these one by one. Memory drives us forward in life. And I found this very interesting definition of memory. And this is not mine. This is the way it's there in the internet if you search. So it says that it is an interlinked cognitive storage space for our past knowledge and experiences. So you have to sit down and think a little bit about it, what this means: interlinked cognitive storage space for our past knowledge and experiences. But in physics, and there are a lot of physicists in the audience as I saw, magnetic memory, that's residual magnetization, or for instance, semiconductor memory. These are all well known and largely used in various devices as well. But what I am going to talk about today is how these three very simple words have a meaning in the context of the physics of gravitation. So that is what is the aim of this talk, to tell you in very simple terms what exactly shadows correspond to in the context of gravitational physics. How can echoes or echoing signals occur in gravitational physics? And how does memory arise in the context of gravitational physics? And if you search the literature of the last 5 years, you will realize that these three words have actually gained prominence in research in gravitational physics. So let me tell you how. Out of these three, one of them has been observed. It is something that is confirmed through observations, although there are debatable questions. An expert will know about what those debatable questions are. So the claim is that we have observed what are called black hole shadows in a galaxy which has a name called M87. Okay. And there are theoretical constructs for shadows of various objects in various theories, and there's a lot of work going on. So that's about the context of shadows in gravitational physics, in astrophysics in particular. In fact, there is a claim that we can see black holes, see within quotes. We can see black holes through their shadows, and that's what I'm going to try to tell you about a little bit. The other two, that is echoes and memory, are not what has been observed, but there are proposals. And there are predictions specifically in gravitational wave physics. And I'll tell you what is gravitational wave physics a little bit. And there are gravitational wave echoes which are predicted from certain objects which are not black holes. These are called exotic compact objects. And people don't know whether they exist or they do not exist. And if they exist, one way to find them out is to look for gravitational wave echoes. And many of those objects, such as objects like wormholes, certain Grava star objects, quantum corrected black holes, these can give rise to the phenomenon of echoes. Then there are predictions on gravitational wave memory also, which I will talk a little bit about. And there are constructs and analysis with a lot of observational prospects in future. So let me turn to each of these one by one. So the talk has three parts. The first part is on shadows. So let me start with everyday life. So lights over here, there's now computer science a lot shadow of arbitrary first in 1969, and this is what is called ray tracing. So the name given to this method, the exact method of finding out the shadow of a complicated object, given that it is illuminated, is called ray tracing. And this is extensively studied in computer graphics with appropriate programs. So that's an aside. So how do you find shadows? Let me tell you a bit of this tracings. So here there's a block over here, and there are these lines which are called the shadow perspective lines. And these shadow perspective lines essentially intersect a line from the horizon light point with just drops from here. And from that, by these intersections, you can construct what is called the shadow of this block when it's illuminated over here. Similarly, you can have shadows in this manner as well. It's the same thing once again. You draw these lines, you draw the horizon lines over here, and then the intersections give you the shadow. But the point is that all of these constructions rely on the fact that light travels along straight lines, which is called rectilinear propagation of light. Well, eclipses are there, the Earth's shadow on the moon, That's also understood in high school. You know, you understand that in high school. Also using rectilinear propagation of light. There is the solar eclipse, the moon's shadow on Earth, and that's also understood in the same way. But then, what we would like to do is to talk about the shadow of a black hole. And if you recall the previous talk by Daniele, you will remember that the representation of a massive object, the exterior of a massive object, like a star, for instance, in general relativity, is through what is known as a curved space-time. So the black holes, as we know, is a possible by Bernhard Genzel and also by Andrea Ghez, which won them the Nobel Prize in 2020, and it also helped in a certain way to help Roger Penrose wins the 1965 Nobel Prize, because unless it's observed, the Nobel Committee is not going to give you an award, even though it might be a very elegant proof as such. So 55 years later, Roger Penrose gets the award for a remarkable 2.5-page paper where he proved the existence of a black hole, in a broader sense, of course. But the image of a black hole may be possible through its shadow. And if you give the search for black hole in the internet nowadays, you will see a picture which I'll show you a little later. And that's the picture of a shadow. Well, shadows of black holes were first thought about by someone called J.L. Sin in 1966. And he was the first person to actually calculate what has been called a shadow today. So let me show you a little picture. So this is, I think everyone knows about the XYZ coordinate hole is a curved space-time, and that's why the light ray that I have drawn over here is not a straight line as such. It's a curved path, and this is what is due to what is known as the deflection by Eddington in 1919 to prove general relativity. That was the first test of general relativity. And it's the same deflection of light which makes this trajectory curved over here. So I said there's a curved path of a light ray, and you draw the tangent from the observer here, and you see y, z, or this alpha, beta, and you can find out what So GW 150914 is a binary black hole merger with masses 36 and 29 solar masses, and we get very good statistics. The question is, can we expect other type of signals? Where will they originate? And what we are expecting, as people have found theoretically, is there could be signals which are echoing, that you can see that this goes down, but then it rises to a lesser height and then it gets a smaller height and so on and so forth. So you see distinct echoes. Okay, but why do we see echoes? If the end state is not a black hole, could be a wormhole, could be a quantum black hole, generically classified as exotic compact objects. Now, it has been found that such ECOs can yield echoing signals. Why? Because if you take a ECO and you give it a perturbation, a disturbance with a wave, you will realize that that wave is going to encounter something like walls, a double barrier potential in technical parlance, but something like walls. And if there are walls, as you know from your mountain experience, you would hear echoes. So that is what is a double barrier potential, like walls over here. And if you look at the signals that emerge, if there is a double barrier potential, then you will see these distinct echoes. And that happens for wormholes and gravastars stars and not black holes. Okay. Well, it's like multiple reflections in a cavity as such. So if you have a cavity, then you have an event, then it gets reflects, and you have a first echo, then you have a second echo, and so on and so forth. So that's exactly what is happening. But that gravity is created by the presence of something which is not a black hole, but it could be an exotic compact object. So these are all predictions. And out of those 50 gravitational wave candidates that we have seen in the last month, people have been busy trying to analyze them and finding out whether there is any echoing signal. So that's the excitement. So there are claims, no confirmations, and echoes will play a decisive role in finding out if ECOs or black hole mimickers exist, but we have to wait. Finally, let me turn to the last bit, which I'll be very brief, and that is about memory. So what is memory? As I said right at the beginning, memory is an interlinked cognitive storage space for our past knowledge and experiences. But I'm going to talk about gravitational wave physics and memory in gravitational wave physics. And there it is defined as the change in the separation of particles caused by a pulse. So if there is a pulse, and initially there were a pair of particles, say sitting together with a difference in their locations, and there is a burst of a gravitational wave, what happens after the pulse has gone? When the initial separation is 0 and the final separation is non-zero, then you say that something about that gravitational wave burst is encoded in that separation, and that is what the separation remembers from the gravitational wave burst. So this was pointed out by someone called Zeldovich, a very famous scientist, in 1974, and later taken up by Braginsky and Grishuk in 1985, who coined the word memory effect. And they provided a very simple analysis. This will be with a couple of equations, so don't get scared. Take a weak gravitational wave, suppose along x direction. The question is, how does the separation between two particles change due to the gravitational wave? So you take one particle at the origin, particle true at some L1, L2, L3. So I have an initial separation, and I want to see what happens to that separation after the pulse has left. So this is called deviation in technical language. X, Y, Z are the coordinates that measure the deviation in time. And the total displacement is very, very small. So you can write the deviation in terms of another quantity, which is called xi u. U is like time. YZ deviation equations essentially reduce to an equation which is like Newton's second law. This is like your left-hand side, and acceleration, this is like your force. Now, if you say that the forcing is over a small interval of time, and you can do something which is called an integration of this, you can realize that Xi2 minus Xi1, which is the separation between particle 1 and particle 2, is not equal to 0, even though initially the separation was different from what it is after the pulse has left. So if it's initially 0, then it is non-zero later on. So separation between geodesics or trajectories, for instance, changes after the pulse has left. That is in a region where there is no pulse. So change in separation due to a pulse when initial separation is, say, 0, is what is memory. Well, you can see this in another way. You have a ring of particles. The gravitational wave is propagating perpendicular to your screen. And that ring of particles, if there is a gravitational wave with memory, that ring of particles will change forever to an ellipse. Whereas if it's without memory, even after the pulse has gone by, the gravitational wave has left, it will come back to the circle. This is called shearing in technical language, and you get a permanent shear memory effect for particles. This is Markov, and this actually can be seen in future. So here are plots, simple plots from some other investigations where this green lines over here tell you about the presence of the pulse, and you see there is a separation between two pulses, two trajectories, and that separation changes. This is called placement. Similarly, if you think of the derivative velocity, that can also give rise to something called velocity memory. So there is a difference in the velocities of the two trajectories after the particle is left. So there's a jump in the velocity called by a pulse, and that's memory. What about detections? Well, this is the signal that I showed you right at the beginning of the gravitational wave business that I talked about a little bit. Now that signal is the blue signal, no memory. The signal with memory is different. It's a little different. That's the red signal. And the memory slowly builds up during one phase and grows rapidly during the merger and saturates to a finite value. So you see there's a difference between these two signals much later as well. So it's an overall tiny DC effect. And what are scientists expecting? That's remarkable. Why is it? Because you remember those Michelson interferometers. A change in the arm length of the interferometers caused by a pulse is going to be there even after the pulse is gone. So something is retained by that interferometer. And that's because of the gravitational wave pulse, which had come with memory. And it has created a permanent change in the arm lengths, which you cannot remove. So that's what people are trying to detect. And there are various experiments. For instance, these are the various experiments. You can see this is H versus frequency. This line over here is one set of experiments in this frequency range. And this line over here is another set of experiments in this frequency range. And there are various candidates which can actually produce these signals, and people are trying. For instance, there's a project called the Einstein telescope, which is hoped, or advanced Virgo or advanced LIGO or A+. These are supposed to detect some of these memory signals. There are traces, BH binary with this mass and BH binary with this mass at this distance. But the strain amplitude, that delta L by L, is let me now conclude. So I told you about phenomena, which we see almost every day in our everyday life. And my objective is to tell you that these three phenomena, which we see every day and everyone is familiar with, have actually made a mark in a different context over the last 5 years. Shadows have already been seen, and you have seen a black hole, and you will see more. It's a proof of existence which is very direct, because you see an image, but we see the shadow. If we see echoes, then we will be seeing exotic objects of various kinds. We will know about their existence. If we don't see them, they are gone. So whatever theory you do is not there anymore. Memory is a crucial phenomena, and that detecting the memory, and I will not go into details, amounts to detecting something called a soft graviton. The graviton is the analog of the photon for the case of the gravitational force or interaction. So hopefully many new results forthcoming, maybe next year. And let me end by a lighter remark. Well, if you search the internet, you will find Northwestern University cello ensemble called Shadow, Echo, and Memory. And what do they say? Shadow, Echo, and Memory is a collection of 19th, 20th, and 21st century music arranged and written for the cello ensemble. Altogether, this varied group of compositions explore the press, and these are textures to bring southern and to aid a listener in revisiting their own history. Thank you.
Well, thank you very much, Professor Sayan. Wonderful. You can about creation of God, how things work in this extraordinary expanse of the universe. You also took us through some exquisite experimental techniques that are being used, and I am amazed to see the vast span of these the LIGO experimental setup. Like we are familiar with the mirrors and lenses in microscopes, but what you showed is there are questions, of course, and so I will open up the floor for the questions. But in the interest of time, I would limit the questions of 2 questions per participant. I can see that Dr. Sayan Chaudhary has a series of questions. So, I'll first just open 2 questions of Professor Chaudhary, Dr. Chaudhary, to Dr. Daniele Oriti. And if I choose in the order of the questions were asked, so I can go in that line. So the first question from Dr. Sayan Chaudhary to Daniele Oriti is this one. He asked, like, from where the general notion of bouncing cosmology came. He says that we can't see the other side before the Big Bang. So how do we know whatever we theoretically are proposing are correct?
I dispute the first statement. In these models, it is possible for signals in the expansion phase, so in the contracting phase, to have consequences on the expanding phase in which we live. In particular, depending on the specific model, you can have imprints of the previous contracting phase in the CMB spectrum, exactly in the picture we see with those satellites of the cosmic microwave background. So depending on the models, the fine details of that picture may differ. And so these models are falsifiable and testable by cosmological observations.
Mm-hmm. And his second question was, apart from having the big fight between the LQG and string theory, according to your opinion, what should be the correct approach to construct a viable, correct, possible theory of quantum gravity?
Oh, but what I work on, of course. Otherwise, I would work on something else. No, no. I mean, I think it's the wrong question. With all due respect to whoever asked it, the problem is exactly the fighting mode. I believe that if any of the current theories of the current proposed formalism will look the same as in 20 years, it means we are dead as a field. Because it means there was no progress, that somehow there was no real improved perspective. And that applies to any of the current approaches, being strings or loops or group field theory or discrete gravity, you name it. And in fact, I also believe that the best way to make progress is to try to see what is going on in the other formalism, whatever is going on. Try to discuss ideas, or if there are problems that in your formalism which are called some more success in the others, and try to learn from each other. Now, this sounds very, I mean, it's like a diplomatic, hypothetical answer. Most of the others, we better learn from each other and go beyond what we already do.
Anyways, your slide which showing the fight, it was excellent.
And I haven't shown any blood.
Okay. Of Dash, and he asks, is there any way to visualize quantum gravity other than the gravity-induced quantum interference?
Say it again, sorry. It's for me, the question.
Yeah, it's for you.
Yeah, I think you can see it in the chat box, actually.
Yeah, is there any other way to visualize quantum gravity other than the gravity-induced quantum interference?
Visualize, you mean the experimental test, I guess.
I guess.
So there is a whole field of so-called quantum gravity phenomenology. So, I mean, the echoes in gravitational waves or quantum gravity produced exotic compact objects that were mentioned in the other presentation are one context in which, in principle, you can have experimental effects from different quantum gravity approaches, depending on what they say about black holes and collapsing matter. Cosmology is what I was mostly referring to, is another context. As I said, what we see in the CMB in the fine details depends on what happened at the Big Bang. In different approaches, it depends to a greater or lesser extent, but in principle, you can see quantum gravity effects there. And then there is a number of other scenarios in which basic aspects of usual field theory are modified by quantum gravity effects. And for example, usual symmetries we use in the standard model could be modified, like Lorentz symmetry. And if that happens, there are a lot of phenomena that we take for granted and they are very well verified in the standard model that could be different by quantum gravity effects and potentially testable.
Okay, thank you, Daniel. So then we have a few more questions for Professor Kaur. And again, the first question is from Sayan Chaudhary. He has been the pinch hitter for this show.
Okay.
Is gravitational memory a purely classical concept?
Yeah,
is it possible to think of a quantum?
Yeah, I can read it.
description?
I can read it.
Yeah.
Actually. So it's okay. So what Sayan is asking is whether it's a classical concept. From what I told in this lecture, I just talked about the classical analysis. Okay. But of course, it has quantum gravity connotations. okay, and calculations as well. And that's why at the end I told you that if you detect memory, then you would essentially be detecting a soft graviton. Okay, so that's something which people have proposed and people have worked on. So all this work on the perturbative field theory related work, okay, linearized gravity and so on, that kind of work and the work done by people like Strominger and then Ashok Sen and all that work essentially is related in some sense to quantum gravity, but it's not quantum, it's not a quantum,
No, I just want to
fully quantum calculation.
why I'm asking this question. I was a little bit confused with the fact that, like, few people, those who are working in LIGO, they are also doing some scattering amplitude thing. Okay, and try to taste a little bit some quantum effects of gravity through LIGO and all. So, is it possible? Do you think these days people are?
Yeah, what you're saying is that, as I said, there is a quantum aspect to memory, of course, but a truly quantum memory as such hasn't really been defined or worked on, in my opinion. So ultimately, what you're going to see is, after all, is not anything quantum as such. Okay. And what I spoke about mainly is about the standard classical GR related memory effects. Okay.
Sure.
But if you talk about quantum memory, that really hasn't properly been defined in a truly quantum mechanical sense. Okay.
For example,
neutron star mergers, yes, but I think initial work was largely on black hole mergers, and I'm not fully sure what these 50 candidates that have been seen recently, what exactly they would correspond to. So that is, I think it's still ongoing, and one has to wait for a while to actually see. But yes, it has been seen in the 10 or 11 signals that were discovered initially.
Okay, thank you very much. And I have one question from the side of general audience. The question is to both the speakers, Dr. Oriti and Dr. Sen. For those who are not in this field, someone is engineer doing mundane terrestrial things. Somebody is in in humanities, economics. So what this field of science that you are pursuing, it's almost like it's a pathway to the not only the initiation of the universe, but it's like almost searching for God. So what message do you have for the general audience? What is the contribution of this field of science to common people?
So on, there is a material which came out, which is called meta materials, and it's the craze of today. And all that goes back to that work which he did. And he was thought to be completely esoteric in his work. So you cannot say if something is useless today, it can lead to something which can really become useful much later. And a lot of this work in LIGO, for instance, involves a huge amount of technological advances, parallel technological advances, which actually can become very, very useful for other purposes as well. Just as the internet, I think all of you know where the internet was first created. Okay. So there also it was created in a physics setting. So that's my point, that there is nothing is completely useful, nothing is completely useless. And we have to be open-minded to accept and understand what is good and what is true science, irrespective of whether it's theory or experiment or something which is completely exotic. That's my point. Yes.
Thank you so much, Professor Kaur. I think
May I?
please.
Yes, please. Please.
I would like to come in from the side of the bureaucrats who are sometimes representing the governments who are at least part of those who are financing people like you. And I think it is extremely important. It's extremely important that we do that with basic science. Basic science is the core, and I mean, I'm echoing basically your sentiments on that one, that that this is the source and the field where, not necessarily from every avenue that you're taking, but in the long run, it bears fruit. If you would take the approach that some governments have tried in the past to say we concentrate on applied sciences side and we are only trying to foster and finance those ones, then you have people who have not much of a knowledge in it, taking the decisions on what to finance. That can only lead to disasters or at least into dead ends. It was Calvin who said it in a different context though, but he said if funding had existed the Stone Age, then we would probably have now very sophisticated stone machines and stone tools, but we would never have reached the steel time or the iron time, right? So we need really the creativity that comes from the thinking of basic science in order to make progress in the long run. And I think money spent on basic science is money well spent.
Can I say something? Hello?
Hello.
Hello. Can I say
Can
a
you
couple of things? Yes, yes.
Yeah,
Can you hear me?
please. Yes.
Yeah, I think what Mr. Oster said just now, I think whether you should fund basic science or whether you should fund applied science and whether something will become useful later on, all that basically depends on the attitude of the people or the funding agencies towards science in general. Anything that you really cannot predict what is going to happen or what kind of things will develop in future. So you need people to actually realize that this is something which take off after 50 years. I mean, that is virtually impossible for people to really realize. But then the main point is whether how much we can connect up things. Okay, I'll give you one example which I give to my students. When there's an engineering okay, which all you must know. Okay. Now you think of that, try to look at the and develop and you develop as something which an engineer think about. Which springs are the engineers are going to ask? The scientist is perfectly okay with F equal to minus kx. But beyond that point, understand what is going to be going in the next 50 years. Okay, thank you.
Thank you very much. It's time to thank really and appreciate the two speakers for their excellent talks. And I intentionally raised these questions because I know there will be students and it's a very nice discussion. I hope both the speakers wouldn't take it in the negative connotation, but it's really a wonderful lecture. So it's time to hand over the session back to Sushmita for her closing remarks. Over to you, Sushmita.
Hey, I'll go. Professor Das wants to ask some question. He's, I think, let him.
Yeah, if time permits, I just like
please.
to say a general statement. That is, I thoroughly enjoyed both the lectures. Thanks to both the speakers. Now, the question, which essentially started from the comment by Professor Ranjan Ganguly, I would like to make just one additional remark here. I remember studying this, reading this book, Mathematician's Apology, by Hardy. There, he starts the book by the statement, the most useful subject in the world is most often that which it is most useless for most of us to learn. We know that the number theory, which was considered completely useless, has applications, God knows how many, many things. And went out that an activity was there. I mean, it was equally probably considered useless, and he is absolutely right. So, the funding, when it comes, you do not know about what is considered to be a right finding and a wrong funding. For example, the superconducting super collider, when it is buried in United States, well, whether it was right or wrong, that is a big question. There is a big argument which is there, whether the funding agencies did the right thing by burying the superconducting super collider, or it should have been continued. This argument will continue probably for long, but only the future will tell us whether it was right or wrong. So the funding agencies should understand what just now Sayan, my colleague from IIT, he mentioned, and I completely agree with him. So with that remark, I would once again like to thank the organizers and Shushmita for such a wonderful lecture. It was really a beautiful one. Thanks a lot.
Thanks, Gurda.
Thanks.
Shushmita, over to you.
Yeah, thank you. And now, on behalf of the German Consulate, General Kolkata, I'd like to thank our guest speakers, Professor Daniele Oriti. Can I see him? No, I cannot. And Professor Sayan for such interesting, I should say fascinating, lectures on the evolution of the moderator and participants and the is also on YouTube channel. We thank you with that for the session on the YouTube. Now, I would like to express my gratitude to 4 former Humboldt Fellows, without whose support this web-based science lecture session wouldn't have been possible. They are Professor Abhijit Bhattacharya of Calcutta University, Dr. Shyam Sengupta of ISAR Kolkata, Professor Pulak Sengupta, and today's moderator, Professor Ranjan Ganguly, both from Jadavpur University. And before we conclude this session, I'd like to inform that our next web-based science lectures will be on 17th December. That session will be on medical science. Please look for the invitation. Thank you once again, and good evening.